I start? Maybe. Okay, so thanks everyone for coming. It's really nice to see so many people in this room. I really appreciate it. So basically, since this is a Guile dev room, I thought I would show a little bit of scheme code this time. So you had the opportunity with Ricardo to learn a bit about the user interface of GIGS. And what I would like to show you is what makes it different. You know, you can always use GIGS from the command line. That's what we do most of the time, or from Emacs, which is very important. But there's more to it, right? You can use GIGS from Scheme, which is sort of like a command line in the end, and it allows you to do more things than you would usually be able to do with other tools, right? Welcome. So. Okay, I think Chris is going to laugh at me with this slide. I'm really sorry. But probably you've seen this phrase before. We're claiming that we're building the Emacs of distros. And it's not just because we're nerds, I hope. Okay, I'm a nerd, but still. I mean, it's all about being able to actually hack the thing and understand how it works and be able to, to fiddle with it and get into the internals. And we really want to have to blur the distinction between users and developers, right? I mean, you can always stay at the command line when you use GIGS, and you can already do quite a lot of stuff, but it's very nice, and I hope not too hard, to actually dive into the scheme interfaces for GIGS. Like Ricardo showed us an example of how you can customize a package definition, right? I mean, package definitions themselves are like, it could be XML, right? It's purely declarative. And then you can start modifying it, and you're actually writing scheme code, hopefully without noticing. And that's the whole idea behind GIGS. So it all goes back to what Stallman was attempting to do with Emacs back in the day, which is that, Emacs is programmable, and the idea is that people would start programming without noticing. And that's really what we're trying to do. So, yeah, I'm going to show a little bit of that. So, there was a talk by Mako at LibrePlanet last year, I think, where I was mentioning, well, user freedom is really two things. We have access, that you're able to actually have the software and to use it in any way. And there's empowerment, which is the third and fourth freedom, that you want to be able to distribute, to modify the software to do what you want, basically. And this is empowerment. And Mako was saying we're doing pretty good with access. I mean, everyone is using free software, maybe not everyone, but a lot of people are using free software, unfortunately sometimes without knowing. But we're not doing so great at empowerment, because it remains hard to modify most pieces of software, right? And so GIGS in a way is a humble take on this part. We're trying to make it easier to get into the software and actually modify it, so you can have practical freedom. You can actually know what's going on and modify it. So I think to get some sort of a guided tour of what's inside GIGS in terms of APIs, we could start by looking at this command and ask ourselves what's going on when we type this. So as you've seen before, this command is supposed to install Emacs and Guile in a single transaction, right? So what's going on? So my goal here is to allow you to get a feel of what the interfaces are, what they allow you to do, and if you're a seasoned scheme programmer, maybe to give you, to allow you to go further. Okay. So first thing, so don't hesitate to interrupt me when I'm making demos and examples. We'll see how it goes. So first thing you might want to be able to do when you look at this thing is how do you actually access packages themselves, and how do you look up a package? So I should have mentioned before, but the way it all started, the way GIGS started is that I was a Nix user before and a Nix developer. And I was really happy with Nix because it's really awesome. It does a great job. I mean, that's how functional package management got started, right? But I was a bit frustrated because as soon as I wanted to write a tool to fiddle with packages and stuff, it was really hard. And the reason for this is that Nix uses an external domain-specific language. So at one point, for instance, I wanted to write an updater, right? A tool that would automatically update recipes for GNU packages inside Nix. But to do that, I had to use the Nix exporter, which would export the Nix syntax tree to XML, right? So all the distribution to XML, and then to parse that XML to just extract a bunch of packages so that I could actually do that task, right? So that's pretty tedious and inefficient and everything. So I thought, wow, it would be great if we could use Guile directly to do that. So let me give an example. So I'm starting a Guile repo. Can you read it? Yeah, I think so. So the first thing I can do from there is just import gigs. So I import a couple of modules. And I'm just saying I want to use these two modules, these two libraries. And these two libraries are actually gigs and the associated distributions, right? So we have, it's just a normal scheme library, which is cool. So for instance, I can use this module. And if I type core utils, so I asked for the value of core utils. It's just a plain scheme variable defined in GNU packages base. And I see that I have a package object. And that's it, nothing special. Okay? So obviously I can query the package. Is core utils a package? Yes, it is. What's its name? That kind of thing. Fine, but I can also obviously look up a package by name, like I can do what's the package corresponding to this specification, and I'm getting a package object. And this is what I would type on the command line, right? And that's how the command line translates specifications to actual package objects. And I can say, like Guile 1.8. Oh, it's not working. Well, you get the idea, right? So obviously I can do things like iterate on the whole list of packages. So we have a function which is called fold packages, and you give it, we can't read it here, it's below the screen, but anyway, we can give it a procedure and an initial value, and it will construct a list of all the packages, right? So here it's telling me I have 3,000 packages in the distribution, for instance. Yeah, and yeah, I think that's about it. Which one is it? Okay. So with this in place, we can already write a bunch of pretty useful applications. I mean, we have, like, if you go to the Geeks website, there's an HTML page that contains a list of all the packages, and it just trivially implemented just by using these helper functions, right? We can just, browse the list of packages, generate XML from it, and we're done. And we have also several user interfaces. So we have the command line interface, which you've seen before. We have an Emacs interface, and we have a web-based user interface, which is still under development. But already, just because it's just a scheme library, you can already write all these things, which is pretty cool, I think. Any questions so far? Okay. So now I need to talk about the store. So you've seen before in Ricardo's presentation that everything that we build with Geeks ends up in GNU store, right, in this special directory. All access to that store is mediated by a daemon. So what happens is we have scheme code here, which is like the Geeks command, for instance, or my Guile repo, and it has a bunch of libraries loaded. And when I build something, like when I type geeks package -i Emacs and it actually needs to build or to download Emacs, then that gigs command here is going to talk to the daemon and ask it, well, can you build it for me? Or if it's already built, just tell me what this lengthy file name is. And if it needs to build it, then it's going to, well, to launch whatever needs to be done to actually build the package. So it's going to run configure, make install, and so on, right, for Emacs plus all its dependencies. But this is all being done by the daemon itself on behalf of clients. This is so that we get isolations, right? So every package is built in an isolated environment, in a CH root under separate namespaces, separate UIDs, and so on. And so, yeah, that's how it works. The daemon itself works, runs as root, and we have our guile thing running here. So, from Scheme, if we want to talk to the daemon, well, we first need to open a connection. Right, so this is my connection to the build daemon. And I can do basically RPCs, so remote procedure calls to the daemon to ask it to do various stuff. Yes?
Excuse me, why do you need a daemon? Why is it not just a library?
Yeah.
Lock a file or...
So we need a daemon because to perform isolated builds, the daemon needs to be able to make a CH root call and to set up separate namespaces, Linux namespaces, and that kind of thing. And so, yeah, so far it has to...
You could do this with a library? No?
No, because you need root permission to do that. And so we could use user namespaces as was discussed before, but it's still a bit in flux in Linux, like it's not, there are security issues and all that, so we're not there yet. Yes, so for example, one of the RPCs that we have here is add text to store, which says, I want to add a file in the store, okay? And users do not have direct access to the store, write access. So they have to rely on the daemon to do it on their behalf, right? So what I can do is that I can say, okay, daemon, okay, I can do that. And this is making an RPC, a remote procedure call to the daemon. And the daemon, as a result, gives me the name of the file which has just been created. If I open the file, yeah, it's just, yeah, it created the file. So I'm not going to go into details. There are many RPCs I can say. I can ask the daemon, is this a valid file in the store? And it's going to tell me if it's valid or not. That kind of stuff. Yeah, so that's basically, that's one of the main ideas. So fine. But if we're looking at what the daemon provides, it's very, very low level. The daemon itself doesn't understand Scheme at all, right? It doesn't know about configure, make install. So at some point we have to translate from our nice high-level package definitions to something low-level, I mean, instruction that the daemon can understand and actually perform. So how does that work? Well, it's pretty useful to use. So this is a DAG that was generated with the gigs graph command. And it's showing the DAG, the graph of package objects for core utils. So this one is a pretty nice, simple graph. And it shows really the relations between package objects. But if you look carefully, you're probably wondering, well, something's missing here, right? Can anyone spot it? How do we compile all this stuff? Right, so we need a compiler, we need libc, we need grep, a bunch of stuff, right? And so we can actually look a bit further down. So there's a lower level abstraction in gigs. It's called bags. And in bags, a bag is a bit like a package, except that we make, all the inputs explicit, right? So here at the bottom, we have GCC, libc, set, grep, find utils, and so on and so forth. And we're just making it explicit here, okay? But there is still something missing. Can you spot it? Well, it's the same story again. How do we compile these? Right? So, guess what? Yeah. We can actually ask geeks to show also the implicit inputs of those base packages, right? And so at the bottom here, we have a bunch of bootstrap binaries which are pre-built because we have to start from something, right? So if you attended Manoli's talk this morning, that's the whole story. We have to start from something, and this is captured by geeks, and it's here. But it's still scheme, right? When talking about bags, we're still on the scheme side of things. So we are still not at the level of the daemon. And what the daemon understands is derivations, which are low-level build instructions. So it's just, basically you give it an executable and a list of arguments, and that's it. That's all it can do for you, right? And so if you try to plot the, derivations, it's too big, yeah. There are many more nodes and so on. So, how do we get there? Well, so I have my core utils package here, and I have my connection to the daemon, and I can say, okay, what's the derivation for core utils? It's talking to the daemon. Well, it's computing the derivation, sending it to the daemon validates it, and we get that as a result. So this is a derivation object. And we see two file names here. One is a .drv, which represents the build instructions, and the other one is the result, right? So what this is telling us here is that we have the .drv derivation, which are instructions, and this is what we will get if we actually build this derivation. So if we look at the .drv, it's basically a text file that lists all the inputs of the build process, everything that needs to be visible in the ch root, right? And somewhere here, there's a call to the Guile executable that will actually run configure, make install. And then we can ask the daemon to actually build it, if necessary. This is 7. Okay, and it's going to build it, trust me. Okay. Questions? So just to summarize, we have several levels of abstractions. We have packages, bags, and derivations. And we also have other high-level objects that can be compiled into derivations, such as origins. So if I go to, so if I look at my core utils definition, it looks like this, define, blah, 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 package, and so on. And there is this origin thing here, which represents the source code. And it's also something that can be compiled down to a derivation, right? So the derivation for the origin is going to download, well, the core util source code, okay? Okay, and to finish, something a bit funny, I think, interesting. So if you remember this picture, you've probably noticed that there is Guile pretty much everywhere, except here. So this is written in C++. This is a daemon coming directly from Nix, right? We're using the same daemon. But we have scheme here and scheme there, right? So there's a pattern, right? I mean, we want to be able from here to describe code that is going to be run there, right? So how can we do that? Well, Geeks has G expressions to do that. So anyone familiar with scheme here? What's the fraction of people familiar with scheme? Should ask. Okay, most of the audience. So if you're familiar with scheme and Lisp in general, you probably know that it's possible in Lisp to have quoted data structures. So I can say quote mkdir foo, let's say, and this is an expression and I could write that expression to a file and give that file to the daemon so that it runs mkdir, right? The problem for us in Geeks is that usually it's not just foo, right? It's a long file name, and we don't want to write it by hand. So we need a solution. So the solution is G expressions. Let me give an example. So instead of backquote here, I'm going to use this hash tilde thing, okay? But it's similar in spirit to backquote. And you can say, let's say for instance I want to symlink corutils. So I can write something like this, and this is, so you can think of hash tilde as backquote and hash dollar as unquote, comma, right? And this is just producing a G expression which represents, the call to symlink with corutils as an argument and output as a second argument. So output is a special argument. So you know that corutils is a normal variable, as we've seen before, but output is not a variable defined here. It's a special value, which means this is the output of the derivation I'm talking about. Okay? So what's different compared to quote? Well, if we look at the internals of G expressions, well, we can say we can query the inputs. Oh, wait. Yeah. We can query the inputs of that expression, and as you can see, the G expression embeds information about what its dependencies are. And that's how it works. And then we can convert it to... I'm not going to talk about monads today, but it's a topic for another day. I can say, okay, I have this G expression and I want to convert it to an S expression. And that's what I get as a result, right? So the file name has been automatically introduced inside the G expression. So from there, I can make a derivation. I say gx2 derivation, foo, and symlink corutils output. So I'm not going to talk about monads, but yeah. Okay, so if I use gx2 derivation, I'm getting as a result a derivation again. And I can again have it built like this. And this is it. And if I look at the result, well, it's, yeah, you can see it here. It's really a symlink as expected, right? So this is a low-level mechanism that we have to have what we call multi-tier programming, because we have scheme in different places, and we need to be able to describe scheme code which is running in a different process at a different point in time, and referring to items in the store. Any questions? Okay, so just very briefly, I'm going to say that this is going further. Obviously, I won't have time to do it, but this is going down to the level of the operating system declarations. So, as an example, this is the operating system declaration for my machine. And I can say, where's my REPL? I can load it from here. Okay, and I have an operating system here, and again I can build my operating system with, I think it's called operating system to derivation. Is it not? Operating system derivation. Yes. And again, same story. It's evaluating the definition for my complete operating system and returning a derivation that contains everything, right? From, system service configuration, initial RAM disk, everything. Okay, and yeah, this is it. Any questions?
So you say Nix, Dynamic Wix is a successor of Nix, something like that, or a better one. But is it a successor of NixOS?
Yeah, I wouldn't call it a successor.
Yeah.
But yeah, so Gix is comparable to Nix, so it's package management. And then we have GixSD, which is comparable to NixOS, I mean, in terms of functionality. But obviously, NixOS is much more mature than GixSD, and so there are differences. But these are different approaches, both technically and also in terms of goals. Like we're strongly committed to supporting free software, whereas NixOS is much more lax in that respect. So these are different projects, I would say, but obviously with a lot in common. Yes?
Okay, so this isn't quite related to this talk, but since this is second year's talk, I have some questions. And that's runtime. So it's all more or less clear when it's command line, so you just execute it and it's done. But what if I have two different versions of some daemon, like database, and they need to run on different ports so they don't collide? And what if I want, just like if I enter one like environment or whatever it's called, so can I make configure, make it so that if I run, I don't know, like PSQL in one environment, it will automatically like hit one port and one version of Postgre, and if I do it in different environment, it will hit port and different version of Postgre or something, or some scenario like that. So what's the story with like where are the data files coming from? Like, different versions of daemons that run at the same time and
I see.
Separate.
Yeah.
On the files.
So I didn't talk much about GixSD itself, but basically when using GixSD, you provide a specification of your operating system. So that includes everything, all these details here. And one of the important parts is services, system services. So you have a services field, and you just give it a list of service objects. And if we look at this particular list, so this is one that we provide by default for people who want to run like XFCE, stuff like that. And we're just building up a list, right? With screen lockers, UDisk, AVI, all that. So if you want to have two different PostgreSQL services, for instance, you would just call, I think it's called probably Postgres service, basically. Specifying different options. So you would say this one is going to listen on this port and this one is going to listen on that port. And under the hood, it's going to generate configuration files, command lines, everything, such that when you run it, it's just doing what you want it to do, right? Okay?
Okay.
Thank you.
Go.